Lesson 3.1, average rate of change versus instantaneous rate of change. To help start us off, I'm going to sidetrack here to just give you a real-world example. You're on the highway, and say you're on the Mass Pike, and you pass the toll booth at mile marker 40. So that's kind of considered your originating time. And then in 1 hour, you pass the next toll booth, and say it's at mile marker 100. To find what we call your average rate of change, which is basically your average speed, we take the change in the distances, change in position, divided by the change in time. So we would get an average rate of 60 miles per hour. Does that mean over the course of that entire hour you were traveling at 60 miles per hour? It could be if you set your cruise control, but even then there's some fluctuation. And what we care about most in calculus is analyzing rates at a moment, called instantaneous rate of change. So a half hour into the trip, how fast were you going? Were you going 65 at that point? And then a little while later, maybe you were at 55? So what we care about is finding those instantaneous rates, and we're going to work on the development of that. To start, we're going to start with the average rate of change. In calculus, that's the slope of a secant line. Slope of a secant line is the way you've been doing slope all along. It's just a little bit fancier notation that you can see. So m sub secant means the slope of the secant line. Visually, here it is. I have 2 points. This is the A, this is the B, and I'm finding that change in position over change in time if you want to connect it to driving. My function right here is this parabola. We're going to find the average rate of change over 1 to 2. Well, at 1, I'm at 5. In case you didn't have a graph of a function, what you would do is you would plug in 1 to the function. Negative 1 plus 6 gives me 5. Then I want to find my ending time for the interval, which is f at 2. And at 2, I can clearly see I'm at 8 for a height. But plugging it in, I would have negative 4 plus 12 to give me 8. Average rate of change, abbreviated typically AROC. Take your f at b. F at b was 8 minus the f at a, which is 5, over the b minus a. Gives me an average rate of change of 3. If I check visually, 1, 2, 3 over 1, it works out. Everything is matching. Average rate of change from a physics perspective, it is the same thing. You're still finding slope, but again, look at the change in notation. Typically, they might use s or x to represent the position function. And then change in position divided by change in time, just a fancier way to say it, is going to get you your average velocity, because things can go forwards and backwards. So speed would only be positive, but average velocities can go positive or negative. Finding instantaneous rate of change, that means slope at a moment. So from a calculus perspective, what we do is we go to the desired point, in this case 1, 5, and I want to know, well, what's my rate of travel at that particular moment? To help us out visually, we would draw something called the tangent line. Definition of a tangent line is it touches the curve and it models the slope at that particular moment. So a tangent line models the slope at your input value, whatever input value you want to put in. Algebraically, to find the slope of a tangent line, in calculus, we're going to change it up and give it some new notation. So you're seeing f with this little mark. It's pronounced f prime of a, f's derivative at a, f's rate of change at a. There's many different names to say the same thing. Those all really stand for slope at a moment. I'm going to take my slope formula, and the idea behind it is to take this second point at x and move it so infinitely close that the 2 points become 1 point and I can find slope at a point. On my curve here, I right now have the secant line, which we know has a slope of 3. This is a little steeper. It's looking like a slope of 4. So as I move along the curve, letting x approach a, having trouble here, so move my point, if I envision connecting the a to the new x, it would be a little bit steeper. See that visual connection? If I move closer, I would be getting steeper. And the closer I get, the closer to this point at 1, the better the tangent line slope is. From an algebraic perspective, f's derivative at 1, f's slope at 1, f's instantaneous rate of change at 1 is equal to the limit as the x value, any x value, we're just using this one, gets closer and closer to 1. To find it, I take f in terms of x, which is negative x squared plus 6x, subtract the height at the input number, which was a height of 5, and then I divide it by x minus the input number. I take my limit notation, and very important to carry your limit notation down. The overall goal is the same as what we did in limits. This x minus 1 is creating a 0. I have a 0 over 0 when I plug in. That means, algebraically, I can rewrite it to try and get this factor to cancel. I don't like to lead off with a negative, so my first step is to take out a negative. It'll be much easier to factor once we do that. Then I'm going to say the limit as x approaches 1 of, keep your negative sign out there, and then the factoring for this, x minus 5, x minus 1, over x minus 1. Well, look at that 0 over 0 situation right here. Those are canceling. Now I'm focusing on the limit as we approach 1 of negative x minus 5 quantity. Once you get rid of the 0 over 0 in definite form, we take the 1 and plug it in. 1 minus 5 is negative 4. Make that opposite. It goes to 4. Look at that. It's matching the slope of the tangent line at 1. The next concept for this unit is the idea of speeding up and slowing down. I know from physics, a lot of you might have had physics, and this is the physics connection. But from a calculus perspective, what we're going to do is we're going to analyze, because it's all about slope, we're going to analyze slopes of tangent lines, and if they're getting steeper, then you're moving faster. You're speeding up. If the slopes of the tangent lines are getting flatter, you're getting more towards a horizontal tangent, then the object is slowing down. Find the average velocity over the interval 0 to 4. What I need is my input 0. What's its height? I go to my graph. It's looking like it's about a height of 1-ish. Then I go f at 4. Its height is looking like it's about 3. So then the average velocity or the average rate of change, they all mean the same thing, can be found by doing f at b minus f at a over b minus a. We end up with 2/4, which is a slope of a half. So if I connected from here to here, let's see if we have a slope of a half. Up 1 over 2. Up 1 over 2. Look at that. I made it to my point. That average velocity is 1/2. Instantaneous velocity at 4. What we do is now we're going to say f's slope, f's derivative, f's rate of change at 4 is equal to, and we don't know this function, so we're going to do it a graphical way. We're going to take a ruler, so pause the video, get yourself a ruler. Once you have your ruler, you're going to line up so that you have kind of focusing on this point right here. And we want to model the slope there. If you look, it's a decreasing function. And I'm trying to say, at that moment, what kind of a slope does it have? So I kind of split the difference on both sides of the curve as I move my ruler closer and closer, so I can just line it up. So I just graze that point, matching its slope as I graze it. And I got it a little bit too mushy there, but it's an approximation, and that's what we care about. So if I have this point here, where's the next time I'm going to hit a point? Let me make my tangent line a little bit longer, so see if I can go point to point. So there. Okay, I'm almost crossing about here-ish. And these are approximations, so you're going to have multiple answers. Down 3, down 1, 2, 3, 4. So down a total of 7 and over 1. So it's looking like it's approximately a slope of -7. Again, this section is going to be approximations. We should have values close to each other. Find the value of t on the given domain at which the instantaneous velocity is a maximum. We do this different from physics, so you got to pay close attention to this one. If I want the instantaneous velocity to be a maximum, I am looking for the highest slope, like mathematically the highest slope. So that means I see negatives and I see positives. In order to get the maximum, a positive number would do it. So I'm only going to focus between here and here because that's where it's positive. I start off with a slope of 0, I end up with a slope of 0. Along the way, see how the curve is increasing and it's getting steeper and steeper. So maybe right about here I'm kind of centered between those two slopes of 0, and this would be about where I have the steepest positive slope. So I'm going to say t equals 2. To find the value of t on this given domain at which this instantaneous velocity is a minimum, minimum is a mathematical minimum, meaning the lowest slope possible. Well, I have sections where I have negative slopes, so I'm going to look in those because mathematically that would be a negative number. And I'm going to look at the steepness of it. So where do I think it's the steepest? I think at the end here at 5 is where it kind of reaches its steepest slope. So I'm going to say t equals 5 would be where I would have a minimum from this one. Find the instantaneous velocity being 0. That means where at a moment the slope is flat, horizontal tangent line is what I'd be looking for. The curve goes flat here. So maybe at like 3/4-ish, t equals 3/4. And then again, it goes flat up here just after 3. So you're just going to give some value right after 3. So 3.1, 3.2, 3.15, 3.125, 3.26, anything that's a little bit after 3. Is the particle speeding up or slowing down between 3/4 and 2? Well, between 3/4 and 2, that is right here and here. Well, if I look at 3/4, that was a slope or a tangent line slope of 0, and then it starts to increase. It's increasing and it's going up, and it looks like it's getting steeper and steeper as I go up. See how it goes flat, not so flat, getting a little steeper and steeper, and then when I get to 2 it looks like that's the steepest positive slope. So because the slopes are getting steeper, that means this particle is speeding up. From 2 to 3, let's go back up and look. Well, 2 is that positive slope that was kind of at its steepest point. And then look at the curvature of the graph. It starts to curve in the other direction. That curving in the other direction is called concave down, which we're going to get to later. But as it flattens, that's what we care about. Flattening is approaching a slope of 0. Since I'm approaching up from a positive slope to a positive less and less, so I get to 0, that means the particle is slowing down. Estimating the initial velocity of the particle. Well, initially is right here at that 0, 1. And I want to know, well, what's the rate of travel at that original moment? It's some kind of a negative rate, so that's where I was talking about we can have negative velocity. I'm going to take my ruler and line it up so I'm just grazing the curve at that one moment, trying to model its slope right at that moment. Like how much is it decreasing? So right here, if I look point to point, I'm going down 1, 2, 3, 4, and over, it's about 4-ish and over 1. So the initial velocity would be, I'm going to use V for velocity. V of 0. V of 0 is kind of like saying f prime at 0, as long as that function is f. And so V of 0 is approximately equal to -4. What we're going to do next is sketch velocity versus time for our given graph. Well, we have some points for velocity that we've already talked about. The initial velocity we just got, and that was -4. So I'm going to put that point on my velocity graph. We said that velocity was 0 in number 10 at 3/4 and at 3.1-ish. So I'm going to put that in. At 4, we said the slope was -7, so that's right about here. And then I have to connect the dots to kind of come up with some kind of a velocity function. Well, I might want to say a little bit more, because right here that's kind of a big gap, and I don't have any values above or below. So I'm going to go to 2, and let's approximate the slope at 2. I'm modeling it up, so I'm right here at 2. It's a little bit above, but again, it's a model. It's looking pretty linear in that section. So if I go from here, which is like a little bit above the curve, I'm going to figure out, let's go here. So if I match it up, 1, 2, 3, and then over 1, this is a little bit higher up, so it might be a little bit more than 3-ish because I'm starting a little bit higher than I'm here. So let's go with 3.5-ish. So at 2, we're going to say like 3.5-ish. And then I'm going to connect. There is a definite connection between the curve that you have, which is a cubic function, and the looks of my derivative function. Look at that. That is kind of looking parabolic. That is a definite connection, which we're going to discover. So we're going to connect. It's looking parabolic. So this would be my velocity versus time function. The next one, average velocity from 0 to 4. So I want to find position at 4. I'm just noticing something. This graph is labeled V of y. Let's change it to S of t, because we're not analyzing velocity graphs yet. So please change that to S of t. So I'm going to find position at 0, which in this graph is 2. I'm going to find the f of b, so that's position at 4. Position at 4 is 2. Average velocity, or average rate of change, either one, is going to be 2 f of b minus f at a over b minus a. Slope is 0. And if I visually look about these 2 points and connected them as a secant line, it would go flat, which means a slope of 0. Is the particle speeding up or slowing down as we go from 2 to 3? Well, right here at 2, that's the bottom. That's a minimum on the graph. And look at its slope, if I'm bottoming out, is going to 0. Then I look and I'm increasing, and I'm kind of increasing at a steeper and steeper rate until I get to 3. So if I go from a slope of 0 to some positive slope up here, then that means my particle must be speeding up. 0 to 1 is the tricky one. If I look at 0, 0 here, okay, is flat. So my slope is 0. But then what happens is I am getting steeper and steeper as I go. So I'm going faster and faster, and then because it's negative, you would think of it as you are going in a reverse direction. So I start with a slope of 0, and then I'm going faster and faster, but because they're negative, it's going backwards. So this is considered to be speeding up because the slopes of the tangent lines are getting steeper and steeper. Oops. Speeding up. Is the particle speeding up or slowing down as we go from 1 to 2? Well, we have this rate going backwards, some negative rate or speed going backwards, but then eventually going to a speed of 0. Because look at that horizontal, that rate of change is going to 0. This is slowing down. And next what we're going to do is sketch velocity versus time. I'm going to go with all the spots where my slope is 0. Slope is 0 at the beginning, slope is 0 at 2, slope is 0 at 4. That's where my curve is flattening. Well, then what I need to do is figure out, well, what are my slopes? It looks like we have some symmetry going on here. So the positive rate here would probably match amounts for that negative rate. So we're going to try and model what the slope is right here at 1. Now this is looking pretty linear itself. So when you go in, you want to model that kind of rate there. And it looks like I might be hitting up here at maybe like a 3-ish. So I am going to say, because it's negative, we're going to say negative 3. And by symmetry, this one would probably model 3. And then we connect. So again, it's curvy. So it's a polynomial function. It kind of gets chopped off. But I'm going to connect it as if it was another polynomial function. Connect them curvy. Finding the instantaneous velocity at 15 seconds. I go to this one, and this one's labeled x of m. Actually, that should be x of t, because we're dealing with time. So find the instantaneous velocity at t equaling 15 seconds. So I go here, 15 seconds. I'm on this part of a graph. Well, this graph is looking pretty linear. It's like 3 linear sections. So my tangent line, if I drew it, would just be right on top of this line. So the velocity at 15, or you can think of it as f prime at 15, getting used to that calculus notation, but velocity at 15 is going to equal, and let's find the rate of change. So I always look for nice points. There's a nice point here at 10:10, and there's a nice point here at 20:40, and those make up that linear section. So I'm going to say 40 end height, end position, minus 10 over 20 minus 10 is going to get me that approximation for the slope at 15, which is 30 divided by 10, which is going to give me 3. Find the instantaneous velocity at 5. Here I am at 5, that's linear. So now I'm going to use the point 0, 0, because that's a nice point that's on that linear section. I'm going to use 10, 10, because that's on the linear piece, and it connects nicely. Velocity at 5, 10, take away 0, 10, take away 0, looks like a slope of 1. And it matches, because if I rise 10, I run 10. The scale is not the same, so you got to be careful. Rise 10, run 10. That's a slope of 1. Instantaneous velocity at 25. Here I am at 25. That curve is looking pretty flat there, so the velocity at 25 is equaling 0. Are you moving faster at 5 seconds or 15 seconds? Well, you look at the slopes at 5 versus the slope at 15. The slope at 5 was the slope of 1, But look at its steepness. Who's steeper, this curve or this curve? We are definitely steeper at 15, and it has the larger slope. So we are going to say the particle moves faster at t equaling 15 seconds. Sketching velocity versus time is different in calculus than it is in physics. So just be aware of that when you're sketching. We make things into functions, and we talk about functions. So we do not do those vertical line connector pieces that they do in physics. So for a velocity versus time curve, I have 3 definite velocities that are constant. So from 0 to 10, we said that was a slope of 1. So I'm going to go here, and I'm going to say I start with a slope of 1. When I get to the 10, I instantaneously change from a slope of 1 to a slope of 3. So in calculus, we would say, we call that, fancy word, a point of non-differentiability, because we can't find the slope at that moment, because we say you can't instantaneously change from 1 meter per second to 3 meters per second. You have to gradually change that. So in calculus, we say the derivative, the slope, does not exist at these corner breaks. And I would jump to my next slope, which is at 3, again, open. That one goes through 20, so from 10 to 20, I'm at a slope of 3. And again, open, because I see I'm instantaneously going from a slope of 3 to a slope of 0. So what happens there is we say at 20, the slope is not defined. So I'm going to jump down to 20, and I'm going to go to the right and say my slope forevermore on the rest of this graph, actually you could just go to 30 and stop at 30, is going to be 0. Okay? So point of impact, maybe from physics, is what they would have talked about. Algebraically, if we want to deal with average rate of change and instantaneous rate of change, here's what we do. The average rate of change is simply slope. Your book changes again. This is what's going to be confusing to you until you get used to it. Instead of saying A and B, your book says x naught and x sub 1. But if it helps you, just rewrite them and say A equals 1, B equals 2. That's what we're dealing with, input and output. So f, or in this case y, but y is f of x. So f at an input of 1, 1 squared is 1. F at an input of 2, 2 squared is 4. Average rate of change is going to be f of b minus f of a over b minus a. So we end up with a slope of 3. So as we progress from 1 to 2, it's got a slope of 3. If I look at my graph to connect it, I'm here at 1, I'm going to 2. If I connected them, 1, 2, 3 over 1. Slope between those 2 points is 3. My goal is to find the instantaneous rate of change at a given value. So this x naught here, that's the originating value. It's kind of like saying that's the a value. So if I want to find instantaneous rate, instantaneous in calculus is f prime, f's rate, f's slope, that little prime notation, at 1. We would take and do the limit, because again we're taking 2 points to find slope, get them closer and closer so they merge and become 1 point. So we're going to take some x value, right of 1, and we're going to move it towards a value of 1. And then I do my slope formula, because again, slope rates are change in position over change in time. So I need my position, which is somewhere to the right, so its input is x. Well, if its input is x, then the function value is x squared. minus the f at A. Well, the f at A was a 1. My height at 1 was 1 minus the A value. Now we're doing what we did on the first test. The limit as x approaches 1 of factoring, so we can look for that common factor to cancel. That's your goal, that indeterminate form of 0 over 0. You want to cancel it. So then it becomes the limit as x approaches 1 of, cancel, cancel, of just x plus 1. Well, if I input that, that means f's slope at 1 is 2. So it's a little bit less steep than the average rate of change. So let's go down to the graph here. Mark your point at 1. And I want to model the slope right there. So I'm going to take my ruler and kind of envision coming at the point and try to get your ruler so that it matches the slope right at that particular moment. Okay? So I'm going to take, oops, I'm too far in here, hit my point, and I'm trying to model, oops, I think it's off a little. Trying to model the slope, matching the slope right there at that moment. Okay, here we go. All right, and so when I take and do my tangent line, I'm going to check, well, what's the slope here? So connecting here, and it looks like here, it looks like a pretty close to a rise of 2 and a run of 1. So the slope of that tangent line, modeling the slope of the curve, is a slope of 2, which is what we connected up here. I'm going to pause now and save the rest for another day.